continuing again from equations 2.4.4, now we can substitute the Newton's law of viscosity. So the shear stress can be represented in terms of this minus mu dvz per dr, and then continuing from that expressions above. Okay, and then we move the dr into the right hand side. For this particular problem, I want to simplify this to R per R. I mean R over capital R. So I can define the R in terms of the R over capital R. Okay, you don't have to go through this particular way, the same that like the way that I did, but this basically shows you one of the possible way. Okay, once I define that thing, then I can continue again. So dvz will be equal to minus P naught PL R divided by 2 mu L, and then R over R 1 divided by R over R d R per R. So this dr becomes this term in here. Okay, then we continue the mathematical steps. Then we can integrate. And continue again. Make a note in here that this actually the 2 C2 with that is equal to C2. Okay, then we have the boundary conditions. This is used to evaluate lambda and C2. Okay, so the BC1 will be at R equal KR, Vz is equal 0. BC2 at R equal R, Vz is equal 0. Okay, so let's put in the first boundary condition first into these equations in here. Okay. Then this will become KR R square minus 2 lambda square ln KR per R plus C2. Okay, then we can cancel this RR. Okay, and we can simplify this into 0 is equal K square minus 2 lambda square ln K plus C2. And these equations in here we define as equation A. Okay, we put in the boundary condition 2 as well. Two lambda square ln R per R plus C2. Okay, then this one will basically can be crossed. This will become 1, this will become 1. Okay, then 0 will be equal to 1 minus 2 lambda square ln 1 plus C2. Note that ln 1 is equal to 0. So in this case, 0 will be equal 1 plus C2. So your C2 will be equal to minus 1. Okay, so that will be this one. And this we define as B. So once we know C2 is equal 1, then we can also carry on the equation A, and we substitute into equation A. So the value of C2, so K square minus 2 lambda square ln K minus 1, 2 lambda square ln K is equal to K square minus 1. So minus 2 lambda square ln K is equal to minus K square minus 1. And then 2 lambda square minus ln K is equal to 1 minus K square. 2 lambda square ln K minus 1 will be equal to 1 minus K square. So your 2 lambda square will be equal to 1 minus K square divided by ln 1 over K. So from here to here, you need to remember your logarithmic operations, okay? Because log A n is equal n log A. So this basically we get this lambda in terms of the K. Then what we can do in here next is that we can substitute to the expression for tau rz and vz. So basically your tau rz will be p naught minus pl r divided by 2l r per r minus 1 minus k square 2 ln 1 over k r per r. Okay, so this will be your final expression for the shear stress. And if you basically substitute, you check these things into your system. Okay, you bring it to your systems in here, then you should get this shear stress distributions in here. Okay, so it's you have to verify the thing for yourself and you try. And then for your vz, that will be equal to minus p naught minus pl r square divided by 4 mu l r per r square minus 1 minus k square divided by ln 1 over k ln r per r minus 1. Okay, I want to basically continue this one, p naught minus pl r square divided by 4 mu l 1 minus r per r square plus 1 minus k square 1 over k ln r per r. Okay, in here I will just continue with the part where I want to change basically. So 1 minus k square. The other part on the left hand side will remain as they are. Okay, so this will be 1 minus k, this one is square, divided by ln 1 over k ln 1 r for r. Okay, so your final expression for the vz will be, the vz is equal p naught minus pl r square divided by 4 mu l 1 minus r per r square minus 1 minus k square divided by ln 1 over k ln r per r. Okay, then we can get these velocity distributions as a functions of r. Then we can get other quantities of interest. The first one will be the maximum velocity. The maximum velocity in here will be equal to the velocity at r equal lambda r. Okay, so this vz max is equal vz at r equal lambda r, which is, we just substitute the value of lambda r inside. One minus k square divided by ln 1 over k ln r per lambda r. Okay, note that this term in here is actually 2 lambda square. Okay, we basically go up this one. Okay, you go back into your original definitions for that lambda square. Okay, then likewise we can cross this with this, and then this one can cross with this. Okay, so in here I will just continue on the terms inside the brackets. So this will be 1 minus lambda square minus 2 lambda square ln 1 over lambda, and carries on 1 minus lambda square 1 plus 2 ln 1 for lambda. Okay, 1 minus lambda square 1 plus 2 ln lambda minus 1 minus lambda square 1 minus 2 ln lambda 1 minus lambda square 1 minus ln lambda square, and then the final expressions will be p naught minus pl r square divided by 4 mu l 1 minus lambda square 1 minus ln lambda square. Okay, and in here please remember that your we have using logarithmic rule that log a n is equal n log a. Okay, I will continue the next quantity, average velocity, on the next video. Thank you.